So once again, a warm welcome from CIA to this webinar. And I will like to introduce myself briefly. My name is Holger Zeltwanger. I'm the managing director of the CIA since 1992. And I also the initiator of this nonprofit CAN user organization. My my professional background is I'm an electronic engineer, and I also worked as an engineer, as a journalist for more than 40 years. I'm still a member of the CIA board of directors, even if I'm already retired. I'm also convener of 2 working groups in ISO and expert in different other ISO committees, as well as in IC, DEAN, and SIE. This means normally I have several hats. Of course, the head of the CIA, the head of the ISO, and sometimes also the head of the SIE. Today, I'm speaking on behalf of CIA. Let's start a little bit with history. Early in the 90s, when the CAN protocol was introduced and realized in silicon, car makers started with simple networks. You see here an example from 1995, so it's a couple of years ago, where 5 nodes were connected in a tree structure. In those days, it was more or less quite simple, and just a few engineers designed the entire in-vehicle network. Over the time, there was introduced step by step more and more electronic control units which are connected to in-vehicle networks. Most of them were connected to CAN-based networks, but there was also coming other networks in the game like LIN, like FlexRay, and last but not least, Ethernet. You can regard this traditional kind of in-vehicle network architecture as a patchwork. You started simple, and then you added step by step another piece. And at the end, you have had some chaotic network architectures with a lot of gateways, with a lot of engineers which were trying to keep the entire system consistent. Beginning of this millennium, there was a new trend. And the new trend was named domain-oriented in-vehicle network system. Typical domains, and this was a software approach, was advanced driver assistance systems, body comfort, connectivity, powertrain, etc. This was a good idea because then you have had you could simplify the system architecture and the software. Unfortunately, these networks, or the different components of the different domains, are located in the car, in the front, in the rear, at the right side, and at the left side, and even in the roof. So this means there was a lot of cabling necessary. And with the increasing number of ECUs, this was also not very convenient, in particular if you want to save weight. And cable means weight. We have several kilometers of cable in a car, and weight means CO2 pollution, and CO2 pollution is something what we should avoid in the future. So this means there was a next idea. This idea is still not implemented in cars, it's just theory. This is the zonal in-vehicle network architecture. The idea is very simple. You have 1 or let's say 4 zonal controllers, which are very powerful machines, and they are connected via high-speed Ethernet network. However, you have still a lot of sensors and actuators which are more simple, and they will not be connected directly to these powerful ECUs. So they use, in some cars, some sub-zonal networks, and below that even the traditional ones, like CAN, LIN, FlexRay, or whatever you have implemented. This is, so to say, a more physical architecture, where you really try to reduce the cabling as much as possible. On the other hand, you have to communicate from the front to the rear via one cable, and this needs a lot of bandwidth to support to transmit all the relevant data. So what means this for the subzone in-vehicle networks? What are the requirements? Of course, because we have a lot of different sensors and actuators with different bandwidth requirements. So the network scalability of those subzone in-vehicle networks is very important regarding bit time, data length, etc. Another requirement is the integration of legacy in-vehicle network approaches. So nobody will substitute in one shot all the today's existing networks and communication systems. So this means we need something where we can migrate easily from today's architecture to the future architecture, which is by theory the zonal architecture, but it may be that there are some hybrid systems in the intermediate time. Of course, we need to have an open communication standards from the physical layer to the application layer and even beyond. The car industry wants to have multi-source components and protocol stacks. The automotive industry is also requiring standardized conformance tests. We need to prove that the devices which we develop are interoperable by means of independent interoperability tests. We call them plugfest, and we know them from other industry. And anything should be available for reasonable prices, in particular the components. We also need a robust transmission of signals, which is related to the physical layer. We need reliable data link layer protocols. We want to support multiple higher layer protocols sharing the same cable, because we have just one network from the, or two networks from the rear to the front, and from the right to the left, and maybe to the roof. And because we see that this is, these backbone networks will be Ethernet based, we need also for the subzone networks, we need tunneling and forwarding of Ethernet frames. When we started to develop CAN XL, which is a data link layer, so to say the third generation after the classical CAN and CAN FD, there was some features which we want to have and what the OEMs required. First of all, we learned our lesson from classical CAN to CAN FD. We want to have a backwards compatibility. We need still 11-bit priority ID. This means 2048 different priorities. This should be sufficient in one network. If we want to transport even Ethernet frames, then we need a larger payload. We need a longer data field. So the payload should be 2048 plus something. I will discuss this in more detail in one of the following slides. If we have the need to run several applications on the same cable, we need also to have in the subzones perhaps a virtual CAN ID, so that we can run 2 applications or 3 applications in parallel on the same cable. We learned also our lesson, and we wanted to have we want to improve the reliability by means of a cascaded CRC, which provides a true Hamming distance of 6. Also, this will be discussed in more detail. Because we intend to have a higher throughput, meaning a higher bit rate, we can change the well-known bit stuff rule. And we think that 11-bit stuff rule is something what we can achieve running at, for example, higher bit rates. The stuff bit counter is integrated in the SIC field. Also, this is remaining from the CAN-FD protocol. And we have, of course, as in all the other CAN variants, the start of frame bit and the end of frame bit as we know it. New is the service data unit ID, which is similar to the ether type. If you're familiar with that, this indicates what is, which next layer has been chosen, which protocol has been chosen. We support, as in classical CAN and CAN-FD, CAN arrow frames, and we are not allowing any remote frame transmission. Before we go into the details of the CAN XL protocol, we have to agree on some OC layer terminology. In the past, CAN was not always using the OC layer terminology, but in the future we should do, and we are going to specify the data link layer protocol for CAN XL using these terms. Who is familiar with that? Most of the engineers are, but nevertheless, I try to repeat something. So always we have a payload, and the payload is, so to say, the SDU of the previous layer. So for example, if you have the data link layer PDU transmitted from one node to another node, then you have the payload, and you have in addition the header and footer. The header and footer contains bits and bytes which are in the responsibility of each layer. CIA will support that, and it is already in some of the CAN ISO documents where you see this, but it's not strictly done, and we try to do this more strictly in the future. So you will see that I'm using these kind of terminology. So I will not talk about messages today. I will talk only about frames, and the frames are not the messages, because the message is just the header and footer of the application layer, plus that what comes from the data layer, which is above and outside of the OC reference model. So there are some similarities to Ethernet already in the CAN standard published in 1993. So the ISO 11898 series specifies two data link sublayers as in Ethernet. We have the logical link layer, LLC abbreviated, and it acts as an interface between the media access control sublayer, which is the lower layer of the data link layer, and the OC network layer. So to say, this is our software interface, which we use when we get in from the next higher layer, the service data. And we have the other sublayer of the data link layer, which is called media access control. And this is responsible for moving frames from the LLC sublayer and provide additional protection, in particular, so for example, the stuff bits, the CRC fields, etc. So let's have a look from the upper layer. And you see that we have now the duty when we have the requirement to support all three CAN variants, that this software layer provides all the information needed for classical CAN, for CAN-FD, as well as for CAN XL. The bits IDE, BRS, and ESI, they are not needed for CAN XL, so they don't care, but they will be on the interface available. So if you decide to send, for example, an FD frame, then you have to set the BRS and the ESI bit and the IDI bit distinguishes between the 11-bit identifier and the 29-bit identifier of classical CAN and CAN-FD. What we need in any case is the PID. The PID is the priority identifier, which you may know as the CAN identifier in classical CAN and in CAN-FD. In CAN XL, is this just an 11-bit field? So the remaining 18 bits are available on the software interface, but they are not used for the CAN XL protocol. Then we have the remote frame, and the remote frame needs to be given, and in this case, it is then not allowed to send remote frames in CAN XL. So the FDF bit and the XLF bit, they indicate which kind of protocol you like to transmit. In our case, if we want to transmit CAN XL frames, then both will be recessive. As I mentioned already, we have the SDU field, and this field is indicating which layer, which protocol you have used, so that the receiver knows, oh yes, he has used this network layer or this transport layer or this application layer. You also need an information if you want to secure, or you have secured your data, or you want that the data is secured by means of the SEC bit. We have the data links code, and we need a longer data links code for a CAN XL because we have more data which we can transmit. And if you're using the same software interface for classical CAN and CAN-FD, then this just the four bits will be used, and the other ones are ignored or don't care. We have an 8-bit VCAN ID. This identifies which channel, so to say, you are using, and you may use up to 255 or 256 channels. And then we have the address field, where we provide the address from the software to the data link layer to transmit this via the bus. And of course, last but not least, the LLC data field, which has 0 to 2048 bytes. And this is just, but you can't use this for a CAN XL. In CAN XL, you need to transmit in minimum 1 byte. So what is different with a completely new approach is the separation of priority and address. In classical CAN, as well as in CAN-FD, the CAN identifier field is 11-bit or 29-bit long, depending which format you are using. And it is used for both, for the arbitration and the addressing purposes. In CAN XL, these functions have been separated. We have an 11-bit priority field or subfield. This field provides the uniquely assigned priority of the CAN XL data frame. It doesn't matter which address it has. It is just the priority. In addition, we have the 32-bit address field, and this field is included in the 64-bit hardware acceptance filter of the CAN XL controller. This is an implementation issue. It may contain node address or content indication information. And you can use it, of course, for legacy CAN higher layer protocols. And then you have maybe a source address or destination address as in J9039, or you have the node ID in CAN Open or whatever. But important is that we have now separated these two functions in two different fields. The virtual CAN field is also new. This 8-bit field allows to run up to 256 virtual networks on one single CAN XL network segment, just indicating which of the channels you're now addressing. This enables the implementation of multiple heterogeneous networks determined by the protocol payload type. So, of course, you need, in addition, the protocol and payload information to distinguish which next layer you are supporting. This protocol type field is now called a service data unit ID field. And this is also an 8-bit field. And it indicates the next OSI layer protocol. We intend to define several solutions. Of course, first of all, we have the legacy CAN-based higher layer protocols. Just indicating this is something what is used as it was in the past, and then it will be interpreted as a CAN ID field from CAN FD or CAN classical CAN. We also will have some tunneling of Ethernet frames, because this is intended that you would tunnel Ethernet frames via the CAN XL network. We also can tunnel classical CAN and CAN FD frames. We will support also TCP IP segments, CAN open and CAN open FD, as well as JNA39 messages will also be supported. A range of those identifiers will be used for manufacturer-specific protocols. And on request, we will assign more IDs to other solutions. Also new are the cascaded CRCs. You know that there was some problems with the reliability of the CAN FD protocol. We have covered that with the new approach in the ISO, but nevertheless, we have improved still in CAN XL the reliability of the protocol. So that is that the CAN XL data frame has 2 CRCs. This is the so-called 13-bit preamble CRC and the 32-bit frame CRC. The CRCs are cascaded. This means the frame CRC protects also the preamble CRC. Both CRCs together are able to detect any 5 randomly distributed bit errors. There's no shortcut anymore to a Hamming distance of 2. We have now a true Hamming distance of 6, meaning 5 randomly distributed bit errors can be detected under all circumstances. Of course, this needs to be proved. The University of Stuttgart and Kassel are doing so. The University of Stuttgart has done already some primary research, and the University of Kassel will start soon with the evaluation of the protocol and its capability to detect errors. The CAN XL content field, this is so to say the payload which we provide, comprises different subfields. There's first of all the already mentioned 1-byte VCAN ID. There's the address field, which contains the full or part of the next layer header footer. So if this is, for example, the network layer, then this will contain some information on the addressing. If this is not sufficient for one protocol, you may use also some bytes from the so-called data field. And the 2048 byte data field contains optionally the remaining part of the OSI next layer header footer and the next OSI layer payload, which comes from the layer above. So we have enough and sufficient space to handle any protocol which is today available, and also for the future, including maybe that we run in parallel some safety or some cybersecurity protocols. This data link layer security, this was a big issue in the automotive industry since many years. There's a lot of discussions. We discussed this also when we started with VCAN XL. There was several proposals, several presentations, but at the end we said, it is not our business to specify a higher layer security. We want to have some optional additional data link layer security. We have just established a task force for cybersecurity and VCAN XL. And this task force will specify the SIC data link layer security protocol. And we have had 2 presentations from some semiconductor manufacturers. And mainly they have the same ideas, and we will harmonize them, and we will have then one specific protocol which we use in particular for VCAN applications. This protocol, the security protocol, is indicated by the SIC bit, as mentioned already. If this bit is set, then you know, okay, this data link layer is secured, for example, by the CATSEC protocol. The CATSEC protocol itself features a 4-byte header with cipher control information, the VCAN secure channel ID, and the freshness value. And the trailer contains the 128-bit authentication tag. And in the middle, you have, of course, then the protected data, maybe encrypted or not encrypted. This security is in addition to maybe an end-to-end protection by other protocols on a higher level. So then attackers, even if they can hack something, they have to hack in addition the data link layer. Otherwise, this will be detected. Now let's have a look from the physical layer to the data frame. Here we see now the OSI data link layer protocol data unit. This includes, of course, that what we have received by software from the layer above, and which we provide to the layer above if we have the receiver of this frame. In addition, the transmitter adds the start of frame bit, which is, as you may know, always dominant and indicates that the transmission of a frame has started. We have then an arbitration field of 15-bit, and this arbitration field includes the priority ID, the remote substitution bit, the IDI bit, which is always set by the protocol controller, the FDF bit, and the XLF bit, which comes from the layer above. So to say, this arbitration field is a mixture of payload and of those things which are added by the data link layer as a header, so to say. Also, the control field contains some additional bits provided by the data link layer, and of course the SDU identifier, the SEC bit, and the data links code, which is given by the layer above. The RES XL bit, this is the bit if we intend to invent a 4th generation of VCAN data link layer protocols. And then we have the ADS field. The ADS field is a 3-bit field with 3 bits, AL1, DH1, and DL1. Not to going too much in detail, this is needed to switch from the arbitration to the data phase. Then follows the SDU ID, the 8-bit indication of the next layer, the indication of the security bit, if a data link layer security is applied or not, and the data length code of 11-bit indicating how long the LLC data field is. In addition, we have then the staff bit counter as known from the CAN-FD protocol and the preamble CRC. All this belongs to the control field. Then we have the content field. I discussed this already. This content field can have from 6 to 2053 byte. It contains the VCAN ID, the virtual CAN ID, the address field, which is a 32-bit value, and the LLC data field. The CRC field after the content field, this is used for the frame CRC, and some additional 4 bits to protect the frame CRC. The acknowledge field is not just a 2-bit field, it's now a 5-bit field because we need also to switch back from the higher speed to the lower speed. And this is the data phase to arbitration switch containing the AH1, AL2, and AH2 bits to integrate all the nodes into the lower speed again. Then we have the acknowledge slot as known and the delimiter bit. And last but not least, we have the end of frame field, which is well known from all the other protocol variants of CAN. So let's talk a little bit about the CAN XL physical layer. To make it clear, the CAN XL data frame is transmitted with 2 bit rates similar to CAN-FD data frames. There's no bitrate switch, is always a bitrate switch. One follows the rules of the classical CAN arbitration. So we are limited in the speed to 1 megabit per second, while the other is used after the arbitration in the data phase when only 1 node is transmitting, and we can increase the speed as much as we want. But this, of course, depends on the capabilities of the transceiver, used transceiver chips. So in the arbitration phase, the maximum bitrate is 1 megabit. The selected bitrate determines the network length. So the same rule applies as in classical CAN and CAN-FD. This means the higher the bitrate, the shorter the possible network length, and the other way around. In the data phase, the maximum bitrate is not limited by the network length. It can be 10 megabits or more, depending on the transceiver's capabilities. Okay. Maybe it's not well known that you can use any transceiver for any CAN protocol. This is also the same for CAN XL networks. CAN XL networks can use any kind of transceiver specified in ISO 11898-2 or the CAN SIC transceivers specified in CIA 601-4. However, using those transceivers would limit the maximum speed which can be achieved. For higher bit rates, let's say 10 megabits and above, the new CAN SIC XL transceivers should be used, and they are suitable for those bit rates, and they will be specified in CIA 610 series. We have agreed in a meeting just in the last week that we want to call them CAN SIC XL transceivers. This is not a final decision. Still, some companies may have a veto right, but I think this will be accepted so that we're using the term CAN SIC XL transceivers, signal improvement circuitry XL transceivers. Those transceivers run in two modes, in the slow mode and the fast mode. In both modes, bus biasing is active. In the slow mode, there are dominant and recessive bits as known from classical CAN. But in the fast mode, there are level 1 and level 0 signals. So we have different signal behavior now. The CAN SIC XL transceivers support the medium independent CAN interface, which is abbreviated MICI. So this is needed to guarantee that we have robust communication on the bus lines. To be honest and to be serious with the medium independent CAN interface, which is called MICI, this is between CAN and SIC XL transceivers and the CAN XL protocol controller. This is still under development. We have different proposals on the table with advantages and disadvantages. And the CIA members and the responsible working group or task force has to decide which one should be chosen. I hope that we will do this very soon. It is intended to do this in the next couple of weeks, in maximum some months, but I don't think that we need that long time. Just a few words on the higher layer protocols. The standardization of higher layer protocols is essential to enable interoperability of devices or electronic control units with CAN XL connectivity. Therefore, CIA will specify some STU IDs and the corresponding address field usage. For example, for legacy CAN FD purposes. We will also do this for other. This means we need also to specify several higher layer protocols in the mapping. One of them is that we like to use the ISO 15765-2 transport protocol adapted to the length of 2048 byte LLC data fields. And we will support the ISO to do so. CIA will also specify a multi-PDU concept for homogeneous and heterogeneous application layers so that we can run in one frame different application layers, not only by means of the CAN ID, the virtual CAN ID. We also want to have this within one frame because the frame is very long, and in such a long frame we can run, for example, different information or different application layers which have been used for a long time. Also, we will specify the tunneling of Ethernet frames so that you have an interoperability and not some manufacturer specific implementation of this tunneling mechanism. As with CAN FD, and we learned our lessons here as well, CIA is highly committed to test interoperability of transceivers and protocol controllers in network environments. Therefore, CIA will organize so-called Plugfest when prototype implementation of the CAN SIC XL transceiver and CAN XL protocol controllers are available. We hope that this will happen by end of this year or beginning of next year. So if there's a sufficient number of implementations available, we will start to organize those Plugfest and to prove if the prototype implementations are correctly done or if there are still some issues regarding the specification. Maybe there are some holes in the specification or there are some possibilities to misinterpret the documents. The automotive industry is also requiring conformance testing. conformance testing does not guarantee interoperability, but increases the probability of interoperability. Therefore, CIA will specify for all CAN XL related specifications conformance test plans, as the ISO has done for for classical CAN and for CAN FD. And these conformance test plans may then be implemented by test houses to perform manufacturer independent conformance tests. How you can get more information on that, what we have provided today, because this is the first introduction of CAN XL in the public. You may subscribe free of charge to the monthly CAN info mail, so that you will be informed about news when the specifications are available or any other news from the CAN community. You can visit our CIA website regularly. You can visit the CAN newsletter online, where there are some more product-oriented information is available. You can contact CIA by means of emails. Yes, you can write just the old style emails sending to headquarters, and then we will distribute this internally to the people who can answer the question. You can contact us by phone, by fax, if you're that old as I. You can visit also us on selected exhibition and fairs. In the times of Corona, this is maybe not that much possible as in the past, but we still hope that there will be this year, at the end of this year, some exhibitions which will really take place and not just virtually. You can participate in CIA webinars, this as you have done today, for about 1 hour. And you can participate in CIA Technology Days. This is a longer event, about 4 hours, with different presenters going into much more detail. You can also participate in CIA seminars and in in-house seminars. I think that next year we will have some of those face-to-face seminars again available, as well as in-house seminars, to get more detailed information on CAN XL or any other topic which you like to have in CAN technologies. You can also follow us on Twitter or other social media. And of course, there are other options which we will provide to get in contact with us. So this is from my side, the first information. And now I'm available for question and answer, and I think there will be a lot of question and answers. You may unmute your microphone that everybody can understand your question. If you don't like this, then you can also send this in the chat, and then I will read your question, and then we can discuss this. I have already one question here, and we can start with that. Bit stuffing is in CAN XL the same as in CAN FD and in classical CAN, means after 5 consecutive bits with the same level a stuff bit is inserted. No, that's not right. As I said, we will do this after 11 bits, and we will also have in the, this is just in the arbitration section, and afterwards we have also some fixed stuff bits in the frame. There's another question. Can you provide more inputs for Ethernet tunneling? No, I can't provide this. This is still under development, and I think the document is not yet available. I think Vector is responsible for this part, and they have done some work, but as you know, this Corona has delayed some of our meetings, and I hope this will be available by end of June, beginning of July. Another question is, when do you believe we will see the first implementation on CAN XL in production vehicles? Volkswagen want to have it in the year of 2025, 2026. about this time frame, I think that car makers are interested. Also, the Japanese car makers are very interested in CAN XL as well as the French ones. So we think that CAN XL will be on the road in this time frame from now 5 to 6 years. We need first some silicon, and then we need some hardware. And until this goes into the production line, this will take about five to 6 years. What is the main motivating use case for XL? BTW, thanks for the amazing seminar. Okay, yeah, what was the main idea behind that? The CAN XL is, if you have the low-end cars, you will avoid as much as possible to have some Ethernet networks. And if you can solve some of the problems with networking, more complex networking with CAN, this would help those companies are in volume production. This is not maybe intended in the first glance for the high-end cars. It is more for the low-end cars, and still they have a lot of ECUs to be connected. And also you can use this in zonal architectures as sub networks. And maybe it's in competition a little bit with the 10 megabit Ethernet, and the people coming from the high bandwidth networks, Ethernet up to 1 gigabit and going down, and we are now going up from 1 megabit and 2 megabit and 5 megabit to 10 megabit. Can you clarify existing CAN transceivers are compatible with CAN XL as long as it is 10 megabit? Yes and no. The existing CAN transceivers can be used, in particular those for CAN FD or the SIC transceivers, and I think only those will survive in the long term. They can be used for lower speed. If you're running the CAN XL network just with 2 megabit or 5 megabit, and this is sufficient, you just need the longer frames, then you can use also the SIC transceivers. And I don't have an idea that you will use classical CAN transceivers. You could do that, but I think this will be not the proper choice for automotive applications. There are too many questions. I can't follow all of them. Oh, they are gone in the chat. Sorry for that. I tried to get to in line. Regarding the VCAN field, will it be possible to broadcast to all virtual CAN networks? I have not thought about that, and we may discuss this if this is an option, that you use something between the different VCAN channels. I think there should be a solution for that, and because I think it is just you as a system designer, you may do that, that you indicate that these are all the networks are, so that you can have a gateway functionality, of course, by some means, yeah. So we will think about that. When I'm very optimistic regarding the 10 megabit per second speed, that transceivers will be maybe earlier available than the CAN XL protocol itself. Because I think the technology is there. We're using more or less the technology or mix of technology from CAN transceiver business as well as from FlexRay. So this is not that big deal. What we need is the MICI interface to make a robust communication between the transceiver and the protocol controller. And but we have, as I said, 2.5 solutions on the table, and we have just to select one, and then the people can start to implement that. Yeah, what is the advantage of CAN XL compared with 10 base T1L? What is the advantage of the English language compared with the French language? If you know already some English, then you may prefer also to use American English. If you coming from another country, or maybe Spanish, then and you have the Latin American Spanish learned, then you prefer maybe to speak in Spanish. I think there are some technical advantages from CAN XL, but I'm not an expert in 10 base T1L communication. So I think price could be matter. Maybe that you have not to train the people that much as if you migrate from CAN to Ethernet. Maybe also that there is some more robustness and more reliability in the CAN XL protocol because we are later. So at the end, you can compare them, and it's up to you from which point you came and what you prefer. If there is not BRS bit, when exactly does the bit rate change? And it is similar to CAN-FD where the switch happens mid-bit. No, it's not more mid-bit. So this is different. So the details are not yet specified, but it's clear that we don't need the BRS bit. We have now the 3 bits. You have seen the ADS and the DAS. This means the arbitration to data phase switch. And this is a 3 bits where we change, and so we don't change in the middle of the bit. Again, the question, the comparison between Ethernet, 10 megabit Ethernet and CAN. I think this is clear. This is something more in, not just technical. Okay. How can I do that? Okay, oh, there are more questions. While tunneling the Ethernet payload, say 1 or 2K over CAN XL, how are going to ensure the reliability of data transmission like TCP? Yeah, we're just using TCP. We can use the TCP protocol on the transport layer, and then you can do the fragmentation there. So we tunnel then completely the TCP protocol. So will CAN XL be cheaper than Ethernet? Oh, this is a good question. I think so. It will be cheaper because we may need less circuitries and less gates to implement things. I think the Mickey interface is compared to the MII interface much simpler. And even this already saves some money. And maybe also the protocol controller is simpler than the protocol controller of Ethernet. But at the end, maybe the price is not the only thing, but I think it will be cheaper. Connectors will be cheaper maybe, and the cabling as well. The slides will be given to the registered participants, of course. If the record of the webinar will be available soon, also I hope it will be, but I'm not sure how fast we are doing so. So there are more questions. Can XL extend the payload up to 2048 bytes in which are not preemptible, meaning once a long frame is being transmitted, one must wait for the... Yeah, this is the trade-off. You have to wait before the other frame is transmitted. But you can select shorter frames. You're not forced to use the 2040. You can do it byte-wise, depending on the application. If you have a time-critical application, I would not transmit 2048 bytes in one frame. I would have shorter frames, and then I can, of course, optimize my network for, let's say, low power messages. CAN XL is, of course, real-time control oriented. This is one of the goals which we have. With the big data field and general overhead, even at 10 megabit, the latency might be quite big. Wouldn't this issue limit the use case quite a lot? No, because then you have shorter frames. If you just have to say a short sentence, yes or no, then you don't need to transmit a long frame with a lot of ideas why you have yes or no set. So this is, I don't think this is an issue. The next question is, since CAN XL transceivers have two modes where they can change between dominant receive behavior from hard ones and zeros behaviors, is their control bit sent to the transceiver to switch? Yes, this is done. This is the task of the MICI interface to do this and to provide these changes. The bus topology is possible. This is not a point-to-point connection. This is a real bus architecture which we have in mind, and with this physical layer. So you can have, of course, the bus line topology. You should not have stars and maybe hybrid topologies. Then you may have some limits at the end because of the asymmetry or other things. The most critical issue in those bus topology is the symmetry of signals. The symmetry, this is the issue, and you should have very precise cabling and maybe connectors so that you avoid any kind of asymmetry of signals. If you're going that high speed. Is there any bus length limitation? Yes, the bus length limitation depends on the arbitration phase. And the arbitration phase, when we are trying to access the bus with the priority which we have, then we have a in-bit time response necessary for the bit. And this limits us at 1 megabit per second to, let's say, in real applications to 20, 30 meters, depending on the physical layer components you have selected. This is the length limitation. If you're going for slower speed, let's say in the arbitration phase to 500 kilobit, then we have the same restrictions as in the past. And this, the speed in the data phase does not limit the length, because only one transmitter is sending. Are there more questions? Oh, there are more questions. Are tool vendors currently developing physical layer test solutions? I think those companies participate and or observe in minimum the CIA activities, because most of them are members of the CIA, and then they will provide in time some tools. I think they want to make business. I know from Vector that they are participating and very actively, and I think they will discuss this internally and start development as soon as possible. I can explain level 1 and level 0. This is not a dominant recessive bit, it's a logical 1 and a logical 0. That's the thing. The CAN-SIC protocol will be defined by the task force, this is right. But it is based on some solutions which have been already in place by some semiconductor manufacturers. They're looking very the same. There are some slight differences. We will harmonize them, and so that we have then interoperability between different hardware security protocol controllers. And this is necessary, otherwise you have to choose always the microcontroller from one company, and this should be avoided. This will be an open protocol and can be implemented by all semiconductor manufacturers in hardware. I think it's not a secret. The main income, the main input comes from Infineon and Renesas. Are there more questions which I can answer? Okay, then information from my side. We plan the next 1 hour webinar for VCAN XL in November, I think. In November, there will be more information available, because then maybe even the first specification have been finished, and the prototype implementations, and maybe we have also already some ideas on Plugfest, or we have some experience from first implementations. So if you like if you're not a CIA member, otherwise you can read the documents anytime, then you may join us again in November when we update you on the VCAN XL development. So if there are no further questions, then I like to stop the webinar just 5 minutes after the hour. And yeah, I thank you for listening and for the lot of questions, and we will consider all of them. Thank you.